Chapter 3, Polynomial Functions, Section 3.1, Quadratic Functions. The objectives are to recognize characteristics of parabolas, recognize both the standard form and the general form of these quadratic functions, to recognize how to find the highest and lowest point, called the minimum or maximum value of that parabola, and finally to put this information together and get a full graph of that parabola. Let's put things into action. Standard form of a quadratic function. Standard form is given to be f of x equals the number a times x minus h squared plus k, where a is not 0. The reason why we do not allow a to be 0 is if it is, then y is equal to the number k, which is simply a horizontal line, and that's not a parabola. The graph of the function is a parabola whose vertex is at the point hk. The parabola is symmetric with respect to the line x equals h. I'll draw you a picture in just a moment. The a value determines the shape of the parabola. If a is positive, the parabola opens upward, and if a is negative, the parabola opens downward. Okay, think about it like this. If the a value is positive, then positive makes you smile. So the graph has this shape right here, and it is symmetric right through the vertex. This point here is called the vertex. If the a value is negative, so think when you are negative, you frown, and that would determine the shape this way. Now the vertex is located right here. The parabola is symmetric right through the vertex. And by symmetry, we mean that what is on one side is a mirror image of what is on the other side. Graphing quadratic functions with equations in standard form. So first we determine whether it smiles or frowns, and that's given by the value of a. Second, determine the most important point on that parabola. That's called the vertex of the parabola. The vertex is hk. Now, you have to be a little careful about this, that when you have the function f of x equals a times x minus h squared plus k, you must have a plus sign here. Then this number here is the y-coordinate of the vertex. This can be a little tricky, because here you must have the minus sign present. When you have the minus sign present, that number there, h, is the x-coordinate of the vertex. We'll illustrate this as we put it into action. Also, find any x-intercepts by letting the y value equal 0. That means you're on the x-axis. The number of real zeros are the x-intercepts. We don't count any imaginary roots that may result from solving that equation. In addition to that, we also want to find the y-intercept by letting the x value be 0. That gives us an additional point on the graph. And then we'll plot the vertex, the most important point. We'll plot the x-intercept. We'll plot the y-intercept, perhaps an additional point if necessary to help fill in the details. And we'll connect these points with a very smooth curve and that shape, like a bowl or an inverted bowl. In other words, it smiles or frowns at you like that. Let's do an example. Graph the quadratic function f of x is equal to -1 times the quantity x minus 1 squared plus 4. So first we'll determine the shape of the parabola. We look right here at the a value. That minus sign means it's -1. So since a is -1, when negative you frown, and so the shape is of this nature. Second, we'll find the most important point of the parabola called the vertex. I call it the most important point because it is symmetric right through the vertex. So if you know where it's located, what's on one half is a mirror image of what's on the other half. So the vertex here is HK. Notice that we have a minus sign here present, so H is 1. We have a plus sign here present, so K is 4. So the vertex is at 1, 4. Okay. Next, we'll find the x-intercepts by letting the y value be 0. So take the function, let the y value be 0, and now it's algebra to solve this equation for x. So we'll subtract 4 from both sides, then we'll multiply both sides by negative 1 to take care of that. We'll undo the square by square rooting both sides. Careful when you take the square root, you always get plus or minus. And then lastly, we'll add 1 to both sides. That splits this equation into two solutions. One is where x minus 1 equals positive 2, and the other solution is where x minus 1 equals negative 2. That's why we have two calculations over here. Once we complete that, we have the value of x being 3 and negative 1. So write these ordered pairs intercepts as follows: 3, 0, and negative 1, 0. Okay, so we are collecting this information, and then we will transfer it to the graph to get a picture of that quadratic function. The picture itself is called a parabola, but the name of the function in its algebraic equation is called a quadratic function. Now we'll find the y-intercept by letting the x value be 0. So this is very easy. Small computation. Let x be 0 here. And then you have negative 1. Now careful here in the calculation because you have a minus sign outside and a minus sign inside. Squaring comes first. Squaring negative 1 yields 1. And then the negative of 1 is negative 1. Plus 4 yields 3. So the y-intercept, when x is 0, y is 3, which is yet an additional point so that we can graph the parabola. Let's take a look at what the picture looks like now. So here we have the vertex here, located at 1, 4, and then the y-intercept at 0, 3. We locate both x-intercepts, one at 3, one at negative 1. We know the shape is a frown like this, and we very smoothly, with rounded corners here, draw the graph of that function. If you need an additional point, you could plot, say, 2, which should land about here, or you could plot 4, which would land about there, or you could plot negative 2, which should land about there. Usually, the x-intercept, the y-intercept, and the vertex, and knowing that it's symmetrical about the line of symmetry right here. So that line of symmetry we would write as an equation. Line of symmetry is simply take the x-coordinate of the vertex, 1, and that is a vertical line, so we write x equals 1. That represents this vertical line here, x equals 1, which means the left half is a mirror image on the other side of that x-coordinate of the vertex. That was the standard form of a quadratic function. Here we now have the general form of a quadratic function. The general form is f of x equals ax squared plus bx plus c. Perhaps this is a more recognizable form from your earlier work in math. So let's take a look at how do we get the vertex in this particular case. Remember, the vertex is the most important point. Well, as it turns out, if you know the value of a and b, that is sufficient to find the vertex. To find the x-coordinate of the vertex, we take the negative of b divided by twice the value of a. And the negative sign comes with the formula. So if the b value up here happens to be negative, then this negative of b will turn to a positive number. So just remember that part there. And then the y-coordinate is found. F of minus b over 2a means take that x-coordinate and substitute it into the equation and compute the corresponding y value. Let's look at some more details. Graphing quadratic functions with equations in the general form. So, as before, we'll determine its shape, whether it smiles or frowns. We'll get the most important point by this new formula. It's called the vertex formula. And then also, as before, we'll find the x-intercept, and a little bit further down, we'll also get the y-intercept by letting the x value be 0. Now notice, what it's saying here is if f of x is some number times x squared plus another number times x plus c, when you let x be 0 to find the y-intercept, then every x turns to a 0, and the only surviving value that you get here is c. So 0c is your y-intercept, and that's what it's telling you right here. That's why that happens. So the y-intercept is very easy in the general form. In the standard form, you have to actually do the arithmetic and compute it. Then we'll gather that information, we'll plot the points just as we did before, perhaps an additional point if needed, and then we'll connect those points with a nice smooth curve. So the only difference between the general form and the standard form is the standard form gives the vertex, whereas the general form, the vertex has to be computed. Otherwise, we're doing the same thing. Let's look at a specific detail. And we'll work problem 2. Graph the quadratic function y equals negative x squared plus 4x plus 1. Okay, so first we'll determine its shape. You see right there the a value is negative 1. So since the a value is negative, negative makes you frown, and so the shape is of a frown, like that. So now we know its shape. Now let's get the most important point, which is the vertex right here. The x-coordinate of the vertex is negative b divided by 2a. Okay? A is negative 1, that's the multiplier of x squared. B is your multiplier of x, which is 4. And the c value happens to be 1, which we'll need later for the y-intercept. So let's compute negative b over 2a. That'll be the opposite of 4 divided by 2 times negative 1. Negative 4 divided by negative 2 is positive 2. So the most important point of the parabola is to the right of the vertical axis. Now we need to get the y-coordinate. The y-coordinate is found by substituting the x-coordinate, which we already found, 2, the x-coordinate of the vertex, into the function and manually computing with arithmetic the value of y. And when that happens, we get 5, so the vertex is at 2, 5. In other words, the vertex is in quadrant 1, so perhaps the parabola is located somewhere here. It opens downwards, so perhaps we have 2 positive x-intercepts. Perhaps it's a little wider. We don't have all the details yet. Perhaps one intercept's negative and one's positive. We'll have to see what the y-intercept is and some additional pieces. But I always think about what the picture looks like as I collect the information. Let the picture help you. Let's carry on. Now, the most challenging part is to find the x-intercepts. Here we're using the quadratic formula. The quadratic formula requires that we know both a and b and c. So we first identify those values. We did before. A is negative 1, b is 4, and c is 1. Substitute those values very carefully into the quadratic formula. Compute them very, very carefully, one step at a time. And then continue. Don't forget that the plus or minus here means that we have 2 solutions. The 2 solutions will be negative 4 plus the square root of 20 divided by negative 2. That's this solution here. And also negative 4 minus the square root of 20, all divided by negative 2. And that's the other solution here. Don't forget to write each x-intercept as a full ordered pair. So now we know one x-intercept is negative and one x-intercept is positive. So that is telling us some information about our picture. Here's our rough sketch from before. The parabola has to be a little wider, like this, to have one negative x-intercept, one positive x-intercept. That means that also across the y-axis, probably up here, we'll get that value most likely next. So always think about the picture as you collect the information. Let's move forward. Find the y-intercept. Okay, this one's easy. Let x be 0. Go to the function, replace each x by 0. Notice the c value is what survives. And without the computation at all, we know the y-intercept is 0, 1 because it's always the c value. Notice how that matches our picture here, that right there is the y-intercept of 1. See how the picture helps to drive the math, and the math helps to drive the picture. I always find it helpful to do both at the same time. Now we'll put all that information together and draw the graph of that parabola. Okay, collecting the information, here's the vertex at 2, 5. We got the y-intercept at 1. We got one negative and one positive x-intercept, and nice smooth curve in a frowning type shape. Perfectly symmetric right there through the vertex. If the x-coordinate of the vertex is 2, then the axis of symmetry is x equals 2. And that's how we graph most parabolas. Minimum and maximum value. Okay. What do we do with minimum and maximum values? Well, if the parabola smiles at you, then the vertex right here is the lowest point. And if it's the lowest point, then we have a mathematical word, minimum. And if the parabola frowns at you in this way, yes, that's the vertex, but now that's the highest point. And we have a mathematical word for that called maximum. So every parabola will either have a minimum or a maximum, and that is governed by the value of A. So that's what it's saying right here on the slide. If the A value is positive, then you have a minimum. Now don't confuse, positive doesn't mean maximum. Remember, the A value controls the shape. If A is positive, positive smiles at you in the pictures this way, which means it's a minimum. And if A is less than 0, negative makes you frown, and that creates a maximum. So there is an opposite nature here, but it makes some sense. The value of A is very important. And then what else it's saying here is that the x-coordinate of the vertex tells you where it is located, but the y-coordinate is what we are quoting to be the minimum or the maximum. So you need to get the both x and y-coordinate of the vertex, which we do anyway when we graph these. You don't need to graph them to find the minimum or maximum, you just need to get the vertex. Let's take a look at an example. This is a repeat of what was mentioned on the other page. That's simply a quadratic function here in general form. Even if it were in standard form, we still have to find the x-coordinate of the vertex and the y-coordinate of the vertex. We say that the min or max occurs at this value of x, but the min or the max is the y-coordinate. So the y-coordinate is important because that's the height above or below the x-axis. So that y value is what needs to be quoted as the min and the max. Let's do a quick example. Consider the quadratic function y equals 4x squared minus 16x plus 1,000. Without even graphing this, we can determine, 1, does this quadratic function, this parabola on this graph, have a min or max? And 2, what is that min or max? Very simply, a The value of A controls it all. A here is 4. Since 4 is positive, positive makes you smile like this. Therefore, there is a minimum. We know right away, no math at all. There is a minimum value. Now, what is that minimum value? Well, that minimum value will be found by getting the vertex. So here we are, finding the vertex, identify the value of A and B, substitute it in the vertex formula x is negative b over 2a, simplify and you get 2. That is where the minimum value occurs. Now, what is the minimum value? In other words, the lowest point on the parabola. That's the y coordinate. So take that x coordinate of the vertex, substitute it into the original function, do the arithmetic, and that y value will be the minimum, in other words, the lowest point on that curve. So see how we quote the min value is the y value? And it occurs at x equals 2. So it gives the left right, and it gives the up down. The up down is the more important to quote for the min or the max. Okay. Let's continue just a little more. We have the same quadratic function here as above. Identify the domain in the range. Okay, again, without graphing. Okay, well, we can do this because we already know that the shape is like this. And we also know that the location of this point from the previous slide is where x is 2 and the y value is 984. Okay. Now, to get the domain in the range, well, the domain for any parabola whatsoever is all real numbers. In other words, there's no way a quadratic function cannot be defined. Or you could say the graph extends infinitely and continuously left and right forever. Every single value of x has a value of y. Now the range is restricted because there is a lowest point, but there is no highest point. And range is always written as low to high. So is domain. Low to high, from the left to the right. This is the vertical. This is the y values, the range from the low to the high. And the low point's 984. We can reach that low point. So we have to write the closed interval, including 984, 984, no comma right there, and then up forever to infinity. Never include infinity, it's not a number. So that's what we're explaining here on the PowerPoint slide. The range of the function is the half open, half closed interval, 984 to infinity, low to high. That concludes the PowerPoint slide, and we'll carry on and do some problems.